and applicable than the specific or septic Hermite splines. There is a paper by Mozero or something, I don't remember, sorry name. He has mentioned in his study that Hermite splines of order 3 and order 5 are more important than the higher, are more applicable and easily programmable than the higher order splines. And as I have shown that 20 Hermite splines can be applicable to any type of equation. It can be even applicable to higher order equations also of order 4 and order 5, even order 3, such as KDV equation, Rosenau equation, and Chromato-Shavansky and Fisher-Kolmogorov equations. Quintic Hermite splines can easily be applicable to these equations. Then these are the references that I have used. In the end, I would like to thank BST, ANR of BST for granting me project and financial support to complete this study. My research scholars, Professor Shirala Shetty, who has invited me to this talk, to this conference, and my family. Thank you.
Thank you, madam, for wonderful talk. Audible, madam? Thank you, madam, for informative talk. Audible, madam?
Yeah, you are audible.
Okay, thank you once again for your wonderful talk. Any questions?
Thank you, sir.
Hello, ma'am. Hello.
Hello.
Ma'am, in the beginning, you had used the Crank-Nicolson finite difference method, ma'am. So after converting the differential equation into matrix form.
I'm sorry, I don't understand what you say. Can you write in the dialog box so that I can understand?
Hello, ma'am. Pardon
Hello?
me, ma'am. Can you please repeat once again?
Madam ji.
Yes, sir.
Hello.
Hello.
His question is, you are applying the Crank-Nicolson method. You are converting differential equation into difference equation.
Yes, sir.
That leads as the algebraic equation.
Yes.
And can write it as Ax is equal to B.
Yes, that is Ax equals to B, then it is x into equals to A inverse B. That's why the nonlinear term is quasi-linear.
And his question is, he is asking whether the coefficient matrix is ill-conditioned or well-conditioned, he is asking.
This matrix is well-conditioned up to certain number of elements. If we go beyond 200 or 300 elements, this will be ill-conditioned. Then we have to apply other techniques too.
And one more thing is,
because the conditioning of the matrix depends upon the block structure.
He wanted to use in place of Hermite polynomials wavelet basis, and he is asking.
Wavelet basis can also be applied, and that is a very good technique. But I am not presently working in this technique. But that's true. That is a very good technique.
He is asking which one is good, Hermite polynomials or Hermite wavelet basis.
These are Hermite interpolating polynomials, not Hermite wavelets. Hermite wavelets are different.
Good, good. Thank you very much, madam.
Thank you,
for your wonderful talk. And thank you very much for accepting our invitation.
Thank you, sir. Thank you so much.
See, our students are giving you a very good, big flowers to you.
Thank you, sir. Thank you so much, my player.
Thank you very much, madam.
Thank you, sir.
Thank you, madam.
Good evening, sir. Am I audible, sir? Sir, am I audible? Sir, am I audible? Santosh, sir?
Yes, sir, you are audible, sir.
Okay, sir. Myself, Veeresh, sir, from ROMC Ballari. Now, let me introduce Santosh Subhash Nandi, sir. Sir is postdoctoral fellow, Department of Mechanical Engineering, Faculty of Engineering, University of Techno Metropolitan. Sir, area of interest is functional nanomaterials, nano component, positive, meta-organic framework, Mexina and their electrical, electronic, optical properties, synthesis, characterization of organic polymer, doping to rare earth nanocomposite, and studying their photovoltaic, supercapacitor, sensor, photoluminance and thermoluminance characteristics, gas storage, catalytics, etc. Sir, teaching experience is 8 years and his achievements is received gold medal in geology graduation from Karnatak University, Dharwad, received best overall award for a paper entitled A Facile Synthesis of Poly Hydro Nano Composite for Solar Cell Applications in the 4th International Conference on Advance in Material Sciences 2021, January 2020, organizes a postgraduate Department of Physics, Raja Ramaro Mahavidyalaya Jata for Distinct Maharashtra, India. Sir worked as Assistant Professor in KLE Technological University, Dr. M.S. Sheshagiri Campus, Belagavi, Karnataka, India. Sir has conducted many workshops and is associate with life member of Indian Institute of Scholars, life member of Indian Science and Technical Education, life member of British Society for Nanomedicines, Catalysis Socialist of India. List of paper presented international conferences. Sir is having 4 papers presented in international conference and nearly 30 paper publications in his credit. Sir having 6 patents. With this brief introduction, I welcome you, sir, once again for present, sir, paper.
Nandi sir, very good evening. Hello? ये मधुकर लिंक होता नोड़ हेलो हेलो सर
ಇಲ್ಲ ಸರ್
Sir, very good evening.
Good evening, sir.
And yours is good morning there.
Yeah, it's good morning, sir, for me.
How are you, sir?
Sir, I'm good, sir. What about you, sir?
So your biodata is excellent. On behalf of Karnataka
thank you so much,
University,
sir.
Dharwad, I heartily welcome to deliver the invited talk. Please start your talk, sir.
Yeah, thank you so much, sir. Thank
Sir,
you.
are you ready?
Yes, sir, I'm ready, sir. I will share
Please
my content.
share your slides.
Okay, sir. Okay, fine. I'll share the slides. I hope I'm audible to everyone.
Yes, sir, it is very much audible. Please start the talk, sir.
Okay, sir. Yes.
And then introduce first yourself, where at present you are there.
Yeah, sure, sir. Sure, I will.
ಮಧುಕರ್ ನೋಡಿ ನೆಟ್ ಏನಾಯ್ತು ಮತ್ತೆ ಹೋತ
So just please confirm me whether my slides are visible to you.
Yes, sir. Is it visible?
Yeah, okay, thank you, sir, thank you. Good evening, everyone.
Very
I
good
hope I'm
evening, sir.
audible to you. Good evening, everyone.
Very good evening,
I
sir.
am, yeah, thank you, sir. I am Santosh Nandi, currently a Pondicherry postdoctoral fellow at the Faculty of Engineering, Universidad Tecnological Metropolitana, Santiago, Chile. I joined here last 2 months back here, working as a currently Pondicherry postdoctoral fellow. Today I will be sharing some mathematical perspectives on understanding and optimizing thermochemical energy storage materials, an area critical for the future of sustainable energy. We all know that reliable energy storage is the key to addressing the global challenges of intermittent renewable energy, waste heat recovery, and energy efficiency. Thermochemical energy storage, or a TCES, in short form we call it as, stands out due to its high energy density and long duration storage capability. In this talk today, I will focus not just on the material themselves, like what we use as a material such as metal oxides, salt hydrates and other nanocomposites, but on how thermodynamics, kinetics, and particularly mathematical models help us to predict, design, and improve these system performance. Our aim is to bridge the material science with mathematical tools to accelerate the development of next generation energy storage materials and the systems. With this brief introduction, as you might be knowing about many of you, these are the daily used energy storage devices in our everyday life, which include battery, supercapacitors, or some of the solar cells. Energy storage devices are charged when they absorb energy, either directly from the renewable generation devices or indirectly from the electricity grid. Since they also discharge when they deliver and store energy back into the grid. So here I have shown you some of the examples of energy storage devices, and I keep on talking about more about power grid system. The power grid system refers to the interconnected network of electricity generation, as you can see in the diagram, which include transmission and distribution systems that deliver electrical power from the producers, such as power plants, and to the consumers, which include homes, industries, or a business office. As you can see the graph here, the analysis of heat transfer dynamics in thermochemical reactions with respect to energy consumption, when you consider out of the 100 percentage, the insights of these different energies underscore the interconnected nature of energy optimization, reaction control, and computational modeling in advancing the thermochemical systems. Now, future research should continue integrating these aspects to enhance efficiency, scalability, and industrial applicability. So this percentage keeps on varying depending upon what type of tool you are going to use it, whether it is a mathematical tool or computational dynamics, or whether you are modifying with respect to thermodynamics or kinetics equilibrium. Now here I have taken some data from the newly released International Energy Outlook 2019, which is a reference case of the US Energy Information Administration projects that world energy consumption will grow by nearly 50% from 2018 and 2050. Most of this growth comes from the countries that are not in the Organization for Economic Cooperation and Development. This growth is focused in regions where strong economic growth is driving demand, particularly in the case of Asia. Now, when it comes to the consider of India's energy transition, reflects that it's rapidly growing due to urbanization and expanding middle class. As the world's third largest energy consumer, India's primary energy demands more than doubled from 417 to 937 million tons of oil equivalent between 2000 to 2020. So this energy or the consumption is expected to grow at an average of 6.7% annually from 2024 to 2031, driving a sharp rise in energy demand. Therefore, as a material scientist or as a scientist, reducing these import dependence through renewable energy or through energy efficiency and advanced storage technologies. So which is very much essential for ensuring long-term energy resilience and economic stability in case of India when you consider. Now here I have shown you some of the key applications of thermochemical energy storage systems. So this, as you might be knowing about them, the first one is called as solar power integration. So when I speak about more about thermochemical energy storage, these systems are used everywhere in our daily life, which are making us to use effective integration of solar energy into the power grid. That is nothing but power grid is nothing but which we connect between the electricity generation and to the supplier, that is consumers. And these systems will allow us for the storage of generally which are energy which are used for peak sunlight after the later use. Means particularly when you consider about the evening time or whenever there is a cloud or maybe due to sometimes in rainy season. So thus the solar energy or solar power integration will improve the efficiency of the entire system. Similarly, from the industry waste, this facilitates the recovery of waste heat from the industry process, transforming that waste heat into usable energy, and thus this also enhances the energy efficiency and reducing the environment impact on the society. So these are some of the basic thermochemical energy storage applications. Likewise, if you consider some more applications, the best example again you can find out the battery thermal management and thermal buffering at very high scale in case of grid management. So now we will focus very important part of the presentation, which I can say that maximum of the students will be benefited out of this. That we call it as mathematical foundations of the thermochemical energy storage systems. Now, if I want to optimize any system conditions, I should have the basic knowledge of thermodynamic foundations And these thermodynamic foundations mainly focuses on the principles of thermodynamic, such as enthalpy, entropy, or you consider even uh, change in Gibbs free energy also. In thermodynamics, we mainly focus on three of the principles, which include entropy, Gibbs free energy, and enthalpy, which you might have studied in 11th or 12th standard. And further, when you're dealing about the kinetic modeling, we focus more on Arrhenius equations here, which are again non-linear ordinary differential equations, which influence or which tells us how the reaction order and temperature are dependent. So which will help us to exactly model how the heat storage or release is going to happen. With these thermodynamic principles and kinetic modeling, as a mathematical person, you should use or you should be knowing about how the computational approach will examine the phase transition, such as when you consider the different phases of solid to liquid, or it may be a gas. The computational fluid dynamics or computational approaches will help us understand the material behavior with respect to the various conditions. Now here I have shown you some of the examples which we are using in thermochemical energy storage materials, which includes metal oxides. It may be, you might have heard about calcium oxide, magnesium oxide, or it may be aluminum oxide, or some of the salt hydrates such as amexines or metal organic frameworks. These are all materials which are used in the thermochemical energy storage systems for next generation material, and these systems demand careful consideration of material design and modeling. So since a material scientist, we know how to use and which type of material can be used, but I request as a mathematician, or they should come forward in understanding how the modeling will help us to give the better performance of the thermochemical energy storage systems. So what I suggest is mathematical foundation of is must in order to study the required efficiency, in order to predict the material behavior and different conditions, which enables the system optimization in order to get the maximum efficiency. So as I told about some of the basic concepts of thermodynamic parameters, which include Gibbs free energy, enthalpy, and an entropy. If I want to discuss about them in brief, in thermodynamics, the Gibbs free energy is a thermodynamic potential that can be used to calculate the maximum work done from the system. Whereas enthalpy is the sum of the thermodynamic systems which measures the internal energy and the product in terms of pressure and volume. Whereas entropy is the measure of the energy of a system that is available to do the work. So these all factors are governing how the system is going to work or how the system is going to behave based on the modeling. When it comes to the thermochemical energy storage system, understanding thermodynamic equilibrium is a fundamental phenomenon. The equilibrium state tells us whether the storage reaction is feasible under given conditions and how efficiently the system can store and release the heat. So now you can see the picture here. It shows that as a material scientist, they know the behavior of the material, but they don't know how the system is going to work because they lack in the mathematical part. Now here I have shown you one of the example or one of the equations which is called as differential standing calorimetry equation. It is a fundamental to understanding how material respond to the controlled temperature changes according to the following equation. So as you can see here, the we call it as Q dH by dt, which is nothing but how the heat is going to flow in the system, which is nothing but it is the sum of the addition of sample heat capacity and the heat rating with respect to the function of time at an absolute temperature. So these equations help us to understand how materials are going to respond or how they are going to behave with respect to temperature changes. So it mathematically expresses how much heat is absorbed or whether it is released by a sample compared to the reference, which enables us to precisely understand the thermal properties of the system. Now, what happens when it comes to any thermal applications? In addition to thermodynamics, the kinetics of a material determination is very important, which helps us to find out how fast energy can be stored or released. Even if a reaction is thermodynamically favorable or not, whether it is slow, the material is not practical for the real world applications. Like in the case of when you consider about solar energy storage or industrial heat recovery. So the dynamic heat storage and release behavior is mathematically described using non-linear ordinary differential equations. These equations account for temperature dependent reaction rates, which are changes in the material properties during the reaction, and non-linear response of the system under varying heat flux, or it may be a thermal condition solving these non-linear differential equations, so which will provide us more about the transient energy storage characteristics and help us to predict material behavior and practical operating conditions using these non-differential equations. Whereas in case of Arrhenius type kinetic expressions, which tells us how the sensitive the reaction rate is with respect to the temperature. Thus, finally, by using validation with experimental data to ensure that the kinetic models are validated against the experimental data, we use some of the experiments or experimental techniques such as TGA, also called as thermogravimetric analysis, or some experiment called as X-ray diffraction techniques, or even maybe some temperature programmed experiments. So thus kinetic modeling supported by experimental validation forms the foundation for rational material selection and also optimization in case of thermochemical energy storage systems, ensuring very high efficiency of the system, fast response, and long-term durability. So now we understood there are totally three parts with respect to the system when you consider. The first is thermodynamic principles we need to understand. The second is kinetic behavior of the system. And finally, very important part of the system is numerical procedure in modeling. So mathematical models describing the thermodynamics and kinetics of the thermochemical energy system materials often involve complex non-linear equations that cannot be solved analytically. To predict the system behavior and to guide the material design, we rely on numerical procedures, particularly such as finite difference methods, also called as FDM. So these finite difference methods provides us a practical way to model both steady state and temporary behavior in materials and devices. Like this, we use another critical tool which is called as global sensitivity analysis, which will help us to understand how uncertainties in model parameters, which include activation energy, or it may be a reaction rates, or it may be a material properties, which affect the overall behavior or the performance of the system. So if you know all these three parameters, such as thermodynamic principles, kinetic behavior of the materials and the system, and numerical procedures in modeling, so one can build a device which can give a high performance and also for a long-term durability. So some of the material scientists also use some advanced tools which we call them as computational modeling techniques, or sometimes even machine assisted parameters also. As you know, CFDs involve the use of mathematical algorithms and simulation to predict the behavior of the thermochemical energy storage materials. So these processes will help us to create theoretical and also the models that can be compared with the well with respect to real world problems or real world experimental data. So which will help us to ensure that the theoretical prediction align with the what observations we are going to get it from the experiments. Similar way, now in South America, there are a lot of people who are working on computational modeling and along with the machine assisted parameters. So these two parameters or the two fittings will enable accurate simulation of the complex thermal, kinetic and structural behavior, providing more insight about the material performance under realistic conditions. Ultimately, such techniques accelerate the application in sustainable energy technologies. So whatever the revenue that we are generating or whatever the amount that we are spending on the research, at the end we are focusing more on sustainable energy technologies. So thus it is very important in order to understand the material behavior as a chemist and as a mathematician, we should always focus on some of the mathematical parameters or such as advanced computational modeling, or it may be a machine assisted experimental data. So with this conclusion, mathematical modeling for thermodynamics and kinetics is a vital for understanding and optimizing thermochemical energy storage materials. Thermodynamic principles guide material stability and reaction feasibility, while kinetic models helps to predict heat storage behavior. Accurate experimentally validated models are essential for designing efficient, reliable systems and advancing into energy storage technologies. Now I request the future generations or even the people who are involving in research where material science and mathematics is most involved. So they should focus on designing through modeling. This is the future research which is going on in everywhere, all over the world, which helps us to understand the thermodynamic and kinetic behavior of the material. So they always should involve with the material, innovative development of material, which will help us to analyze theory-based as well as practically based materials that will help us to develop the future energy storage materials. So future application will rely heavily on mathematical modeling to guide the rational design of high performance material. Ultimately, these advancements will enable efficient integration of systems in energy management, supporting renewable energy utilization, waste heat recovery, and storage solutions. So with this brief talk, I conclude my session. I would like to express my sincere gratitude to the Department of Mathematics, Karnataka University, Dharwad, and the organizing team of the International Conference on Mathematical Analysis and its application for providing me a valuable platform. I extend my special thanks to Professor Sharan Shetty sir, Chairman and Director, Department of Mathematics, Karnataka University, Dharwad, for his constant support and encouragement. Thank you all for your attention.
Professor,
Yes, sir.
I wanted to ask you some clarifications. Hello.
Yes, sir. Yes, sir.
What
I hope I'm
I
audible to you,
wanted
sir.
to expect from you, you are highly knowledgeable and very scientific, and you are very good in material science. What I wanted to expect from you, and then two things you are highlighted in your talk. One is regarding the nonlinear differential equations, another one is mathematical modeling. Through mathematical modeling, construction of nonlinear differential equations I want. I wanted to expect from you, through mathematical modeling, nonlinear differential equations I want. And another thing you highlighted in your talk, for solving those nonlinear differential equations, numerical techniques are very much essential. So we are ready with very advanced numerical techniques. Suppose if we apply our numerical techniques for solving those nonlinear differential equations, it is very much beneficiary for the society as well as the, without conducting the experiments in the laboratory, we can analyze the results for solving those equations. Please clarify these things. Sir, is it audible?
Yes, sir. Yes, sir. I'm audible. Sir, you are audible, sir.
What I want, sir, I wanted to expect from you, through your experiments, I want, through your mathematical modeling process, nonlinear differential equations. Have you heard, have you seen anywhere in your work?
Yes, sir.
Nonlinear
We have
differential
seen
equations.
many such cases, like particularly in modeling complex real world problems, you can consider about weather prediction, or whether it is a non-linear heat transfer, or it may be chemical reaction understanding. So these non-linear equations are very much essential for us.
No, I want nonlinear differential equations from your work. In
Okay,
generally,
okay,
I
sir,
know
yes.
nonlinear differential equations, governing equations are available in thermodynamics and all that, heat and mass transfer. But from your work, I want nonlinear differential equations. It is a challenging task for solving those equations. We are ready for solving those equations. So you search such kind of equations and send me some papers. So we will work together. I appreciate your knowledgeable work, and I congratulate you because you presented a very nice talk. And thank you very much for accepting our invitation and grace this occasion. In future, we have to do some serious research work. Now I request Srushti Kulkarni to propose the vote of thanks.
Thank you, sir. Thank you so much.
Thank you, Santosh sir, for wonderful session. I would like to extend my heartful gratitude to Dr. B. Veeresh sir for chairing the session. I thank everyone for patiently attending all the sessions. Here we come to the end of today's sessions. I request Madhukar Kulkarni sir to proceed the session.
Hello, Pavitra madam, are you ready with your online presentation? Dr. Pavitra madam.
Yes, sir.
Then you can share your screen and present our paper.
Okay, okay, sir.
I also request P. Viresha sir to chair this session.
Good evening, madam. Am I audible? Madam, you can start the session now.
Sir, can I start my presentation?
Yes, madam. You can
Okay.
start.
Yes. Good evening, sir. Good evening, everyone. Myself, Dr. Pavitra J.M., working as an assistant professor in the Department of Mathematics, Sahyadri Science College, Kuvempu University, Shimoga. Today I want to present my research article, Analysis of Heat Transfer and Fluid Flow in a Particle-Laden Suspension over a vertically stretching surface under internal heat effects. The abstract of the research article is, this study examines the influence of internal heat generation and absorption and viscous dissipation on the boundary layer flow and heat transfer in a dusty fluid over an exponentially stretching surface. By applying similarity transformations, the governing partial differential equations are reduced to certain nonlinear ordinary differential equations. These equations are solved numerically using RKF method. The impact of key physical parameters on velocity and temperature distributions is explored and illustrated through graphical results. So, the mathematical model, here I am considering a steady two-dimensional laminar boundary flow and heat transfer of an incompressible viscous dusty fluid near an impermeable plane wall stretching with velocity and a given temperature distribution. It is assumed that the impermeable surface is stretched with exponential velocity and in quiescent fluid, and the surface is maintained at a temperature. The x-axis is chosen along the sheet x-axis and y-axis normal to it. Two equal and opposite forces are applied along the sheet so that the wall is stretched exponentially. A uniform magnetic field B is assumed to be applied in the y direction. So these 2.1, 2.2, 2.3 and 4 are the boundary layer equations. Here I am considering the boundary conditions as shown in 2.5. To solve these equations, I am considering similarity transformations, which is shown in 2.6. By using similarity transformations, we get solved ordinary differential equations, that is 2.7. Here, in the heat transfer analysis, 2.8 and 2.9, I am considering the equations along with the boundary conditions given here. So after using similarity transformations, we get the solved equations as 2.10 corresponding thermal boundary conditions as shown is.
Excuse me ma'am, sorry to interrupt you. We are unable to see your slides.
Sorry?
Yes ma'am, now we can see. Thank you. Please continue.
Okay, sir. The system of nonlinear equations 2.1 to 2.4 and 2.10 and 2.11 subject to the boundary conditions. 2.5 and 2.12 are converted into a. Sir, my voice is audible, sir?
Yes ma'am.
These equations are converted into a system of nonlinear ordinary differential equations using similarity transformations. These nonlinear ordinary differential equations are then solved numerically using RKF-45 method with the help of Maple software. In this method, we choose the suitable finite value for eta as 5 and we form a table 1 which can notice that there is a close agreement with these approaches and thus verifies the accuracy of our method used. So table 1 is as follows. Here there is a comparison of our results with other authors. In the results and discussions, so here a steady dusty boundary layer problem for momentum and heat transfer over an exponentially stretching continuous surface with an exponential temperature distribution in presence of magnetic field effect is examined. The boundary layer equations are then solved numerically. The velocity and temperature profiles are depicted graphically for different physical flow parameters. A comparison between wall temperature gradient values computed with the present method for these values made with that of earlier authors as shown in the table 1. From the table 2 we can conclude that as fluid particle increases, velocity phases increases in the dust phase and decreases in the fluid phase. Figure 3 depicts the temperature profile for different values of fluid particle interaction parameter. From this, we can notice that temperature decreases with the increase in fluid particle interaction parameter, and also it indicates that both the fluid and dust particle decreases as beta increases. The velocity profiles for different values of the magnetic parameter presented in figure 4, it shows that the rate of transport is considerably reduced with the increase of magnetic field. Figure 5 shows the temperature distribution for different values of magnetic parameter M. We inform from this figure that temperature increases with increases in magnetic parameter. Figure 6 illustrates the effect of Prandtl number on velocity profile. So as Prandtl number increases, temperature profile for both velocity fluid and dust phase decreases. Here figure 7 explains the effect of Eckert number. As Eckert number increases, temperature profile for both fluid and dust phases increases. From this, we can conclude that the fluid particle interaction parameter decreases the velocity components in the fluid phase and increases in the dust phase. As fluid particle interaction parameter increases, temperature distribution decreases both in fluid and dust phase. Velocity distribution decreases as magnetic parameter increases in both the fluid and dust phase. The effect of increasing the value of magnetic parameter is to increase the temperature distribution. The Prandtl number decreases the temperature profile, whereas Eckert number increases the temperature profile. If beta magnetic value and Nusselt number becomes 0, then our results coincide with the results of Magari and Keller, E. Laziz, Pal and Srinivasacharya and Ram Reddy for different values of Prandtl number. Hence the result. Thank you for the opportunity. I would like to thank for the organizers for conducting such an wonderful conference. Thank you, sir. Thank you so much.
Ma'am, can you show us?
Excuse me, sir.
Hello. Hello. Hello.
Thank you, sir. Thank you for the opportunity, and once again, I would like to congratulate for organizing such a wonderful conference, sir.
Ma'am, can you show us the slide where you have used the similarity variables?
Sorry, your voice is broken, sir. Sorry.
Can you show us the slide where you have used the similarity variables?
Okay, sir. These are the similarity transformations, sir. These are the variables, similarity variables.
Ma'am, have you checked whether they are dimensionless or not?
Sorry, sir, your voice is not audible.
Whether you have checked if they are dimensionless or not?
Dimensionless, sir.
Yes, ma'am. Have you checked them?
Sorry, sir.
I'm asking if you have checked whether they are dimensionless or not.
No, sir, in my research work, not yet checked, sir.
Okay. Now I hand over the session to session chair, Dr. P. Viresha, sir.
Thank you very much, madam, for your wonderful talk. Thank you.
Thank you, sir. Thank you so much.
Thank you once again on behalf of Mathematics Department, Karnatak University, Dharwad. Thank you. Madam? Okay, thank you.
Thank you everyone for attending this session. Now you all can exit.